In this video, we'll take a look at the following problem. Suppose that we have a square and we want to find a circular ring, which is also called an annulus, so that the square and the annulus have equal perimeters and equal areas. What is unknown here? Well, since an annulus is a region between two circles and we want to find the particular annulus, then the radius of the outer circle, which we'll call R1, is unknown, and the radius of the inner circle, which we'll call R2, is also unknown. What about A? A is the side of the square, and since we were given the square, A is known. You can think of A as any particular length that doesn't change throughout the rest of the video. And what we want to do is to express R1 and R2 in terms of A. So we have two unknowns, R1 and R2, and two equations, one that says that the perimeters are equal and one that says that the areas are equal. We'll see what each of them does. But first, if there weren't any conditions, that is, if we ignore these two equations, what would that mean? Well, in that case, we could have any annulus. So R1 and R2 could be anything as long as they're both positive and R1 is greater than R2. And in that case, we could change R1 and R2 independently of one another. That also means that if, for instance, we fix the inner radius, we can still change the outer radius. And vice versa. If we fix the outer radius, we can change the inner radius. That would be the case if we didn't have any condition. But we have two conditions, and we'll look at them one at a time. We'll first look at the condition that the perimeters are equal. The perimeter of the square is 4 times A, and in the previous video we said that the perimeter of an annulus is equal to the outer perimeter, which is 2 pi times R1, plus the inner perimeter, which is 2 pi times R2. And this is equal to 2 pi times R1 plus R2. So R1 plus R2 is equal to 4A over 2 pi. And that is equal to 2A over pi. This means that the condition that the perimeter of the square and the perimeter of an annulus are equal actually means that R1 plus R2 cannot change and that it must be equal to 2A over pi. So R1 and R2 can still change, but not independently. They can only change together so that their sum is equal to 2A over pi. This is what that looks like. Here we see that while one radius increases, the other decreases, and vice versa. This is the condition that the perimeters of the square and annulus are equal. Now, let's ignore the condition for equal perimeters and focus on the condition for equal areas. Here too, we won't be able to change R1 and R2 independently, but the allowed change will be different. Here's what we have. The area of the square is equal to A squared. And the area of an annulus is equal to the area of the outer circle minus the area of the inner circle. So the area of an annulus is equal to pi R1 squared minus pi R2 squared. And this is equal to pi times R1 squared minus R2 squared. That means that R1 squared minus R2 squared is equal to A squared over pi. Therefore, the condition that the areas are equal actually says that the difference of squares R1 squared minus R2 squared cannot change, and it must be equal to A squared over pi. So, in this case also, the outer radius and the inner radius can change, but only in such a way that the difference of their squares is equal to A squared over pi. we see that this change is different from the one we had before. In this case, both the inner and the outer radius increase or decrease together. Here is a side-by-side comparison. On the left, the perimeter doesn't change, while on the right, the area doesn't change. So annuli on the left have equal perimeters as the square, and annuli on the right have equal areas as the square. Since we are looking for an annulus that has the same perimeter and area as the square, it should appear both on the left and on the right. Now let's find it. We got the expression for r1 plus r2 from the condition that the perimeters are equal, and the expression for r1 squared minus r2 squared from the condition that the areas are equal. Now r1 squared minus r2 squared is the difference of squares, so it is equal to r1 plus r2 times r1 minus r2. And that is equal to a squared over pi. But r1 plus r2 is equal to 2a over pi, so 2a over pi times r1 minus r2 is equal to a squared over pi. Now a and a cancel out, pi and pi cancel out, so that means that 2 times r1 minus r2 is equal to a, that is r1 minus r2 is equal to a over 2. So r1 plus r2 is equal to 2a over pi, and r1 minus r2 is equal to a over 2. Now when we add these two expressions, we get that r1 plus r2 plus r1 minus r2 is equal to 2a over pi plus a over 2. Here r2 and r2 cancel out, and we get that 2 times r1 is equal to 2a over pi plus a over 2, which means that r1 is equal to a over pi plus a over 4, which is equal to a times 1 over pi plus 1 over 4. This means that we found the outer radius. If instead of adding these expressions, we subtract the second from the first, we get that r1 plus r2 minus r1 minus r2 is equal to 2a over pi minus a over 2. But here, since we have minus, r1 and r1 cancel out, and this minus and minus turn into plus, so we have r2 plus r2, which is 2 times r2, and that is equal to 2a over pi minus a over 2. And when we divide both sides by 2, we get that r2 is equal to a over pi minus a over 4, and that is equal to a times 1 over pi minus 1 over 4. This is the inner radius of our annulus. So if a square and an annulus have equal perimeters and areas, then the outer radius of that annulus is equal to a times 1 over pi plus 1 over 4, while the inner radius is equal to a times 1 over pi minus 1 over 4. And here is what that looks like. The outer radius is equal to a times 1 over pi plus 1 over 4, and the inner radius is equal to a times 1 over pi minus 1 over 4. With that in mind, I leave you with this problem. Side of a square has length a. An annulus has 2 times greater area and perimeter than the square. Express the inner and outer radius of that annulus in terms of a. That is all for this video. If you liked it, click the like button, helps with the YouTube algorithm. And I'll see you next time.